So that was the end of section 7.5. Now we're ending the 7.6, which is continuity. So let me explain how we started this continuity, whole thing at the beginning. At the beginning of the course, I showed you this triangle picture, and so measuring the distance from here to there is just like it was a 2, but it looks like 1, but it was 2, or things like that. Remember that part? So I gave you a lesson. You can't just rely on visual information. You have to do mathematics, logical and algebraical. Next thing I jumped in is a physics problem computing the speed of a moving object. It's a fundamental physics problem, a long time ago. Then in it, that's to make sense out of the speed problem, there's a notion of limit is in there. Now, analyzing this notion of a little bit further, it seems like we're using some sort of continuous motion in there. In mathematics, that continuous motion, you ask yourself, okay, what is this continuous motion? It turns out you have to use this concept of limit again. So that's circular reasoning, right? So we can't use this continuous motion to introduce the notion of limit. So we created the sequence method, sequence idea. All right? So how many sequences are considered in one limit problem? Infinitely many sequences are considered. That's going to replace this continuous motion. So that's how it came about. So now you're using this limit. We try to understand what a continuous motion is. That is something that is naturally introduced and no one really questions when you're learning this in the physical terms. In physics, something's moving continuously, especially the time seems like continuously varying or something like that. So here's my introduction to continuous motion, naturally analyzed in mathematical terms, and here's a mathematical definition of continuity. It's introduced in this way. So here's a little picture I'd like to use to introduce that. Alright, here's a spring system, and here's some mass attached to it, and gravity pulls it down. The tension of the spring and gravity, they settle on and not moving at all. Equilibrium status. Now you have a rubber hammer or something, so don't hit it left to right, just hit it from below to upward or downward. Once you hit that, it's begin to move then, and that's a motion you created. Another interesting idea of Newton is that thinking about this object in here, not as this object that occupying a certain volume of a space, but want to look at it as some notion of a center of mass. If certain physical law is applied, it's kind of equivalent to apply that physical law to just one point, where this entire number of molecules is crunched inside a very, very tiny piece. Let's say it's a very tiny marble that has the same amount of mass is in there. So if you hold that tiny marble, the way you feel the weight is the same thing as the big thing attached to it. Kind of condensed into that version. So Newton thought about that kind of situation. Okay, suppose we could do that in a tiny space, and in there it's very heavy though, right? So we're going to apply, a location and gravity rule just to that one point. So using that idea, mathematically lifted in here. All right, this is called Newtonian space-time. It's not Einstein's space-time. It's Newtonian space-time I'm about to introduce. If I hit that up, downward or upward, what is the movement of that center of mass? It's going to go up and down or down and up, things like that, right? So maybe it's keep moving up and down like that. So it's one-dimensional motion. Very simple, going up and down. But Newton wanted to expand this one over time here. T is representing time. Vertical axis is vertical position of this one. So in our mind, we don't have a formula. In our mind, ft is a function that represents vertical position at time t. Okay? You can make a measurement. At the 0, it was there. I hit it from low to upward, so it began to move upward like that, right? So after 1 second, it was over here, for example. So after 1 second, here's a 1 second. That center of mass was at that located, and we make the measurement at 1 second. After 2 seconds, we make the measurement, and it seems like it's still going up. And after 3 seconds, This time is not higher than that. It seems like it's coming down, but somewhere over here, something like that. You keep measuring that. Oh, how about in between those times? And you can do the 1.5. You make a more measurement, 0.5 and 0.6. Suppose you made millions of measurements, but that's still finite, right? That's still finite. But you can imagine how doesn't matter how millisecond you measured, even in between those milliseconds, probably there are another time space that's in there exists that we have not measured in there, right? So there's infinitely many space and time just pass by. We can only measure just finite of them. So we can just pretend that there are actually infinitely many points. You can, when you sketch it like this, these are only finitely many pixels, and they're so big. If you zoom in, they're overlapping each other. So it's, it has a limitation, but you can kind of abstractly accept that there's infinitely many time spots, so they're all filled in there, right? Okay, so that we don't have a formula, ft, but abstractly, no matter what time period in here, there must be some position that this is going through, right? So we kind of believe that whatever that means, it seems like it's continuously changing its motion. It's not like at one moment in here, and next moment it disappeared and appeared in somewhere else. We believe it is continuously occupying this space, right? So that vague notion of continuity is accepted. Now we are about to give a very mathematical definition, so there's no vagueness or anything. Everything is concretely defined, right? So this motion is accepted a continuous motion. And back then, no one even thought about it as non-continuous, discontinuous motion. But whenever people try to measure the position of electrons, they realize that if they measure even closer and closer in the time intervals, they realize it doesn't seem like they're close to each other. One moment electrons here, next moment is somewhere else. So it's kind of weird. So they begin to have to develop mathematical theory out of this discontinuous function as well. But classical ones are usually just continuous. So that's why the entire calculus is written for continuous motion function. Okay? So here is an example that I prepared. Here's an example. Well, let me introduce this definite idea first. I think that's the order I had in mind. So here's what is the notion of this continuous motion. By looking at this picture, there must be this graph, and we don't know the formula. It's just physical phenomenon. There must be this thing. So we see the existence of function, but we don't have a formula, right? So what is a continuous? This is their idea. F of 2.5. What does that represent in this context? Right, y at 2.5 seconds. So vertical position at 2.5 seconds, right? So we can imagine, we don't know exactly what that is, but we can imagine, okay, that's the position at 2.5 seconds. And their idea is that what if the position right before that would be 2.49999, right? That will represent the position of the center of mass at that time spot. How about this one, f of 2.5000002, things like that. That's the position of this thing right after that time 2.5, right? If it is continuously changing, what would you expect the relationship between these three quantities? They're not equal, right? But they're very, very close to each other, don't you think? How do you express that, all this vague notion, into concrete mathematical term? What would be the idea? Okay, this can be probably well summarized that f of 2.5 is equal to what? This is something we have been looking at all these 2 weeks. F of 2.5 must be equal to limit, thank you, limit of t approaching what? 2.5, the position f of t. Make sense? Okay. If you happen to have a formula, right now we don't know the formula. If you happen to have a formula, and if that happens to represent motion, that motion must have this property. It's continuously changing. The position around that point 2.5 seconds must be awfully close to 2.5. And this is the mathematical definition of this being continuous motion. Everywhere, it does not matter 2.5 at 2, 1, anywhere here, if you stick that times c, this must happen. That is the mathematical definition of a function being continuous. All right? So here is actually definition written for you. How can we observe this type of thing? You actually have to write down everything that is written here. So it is not exercise today, but I want you to look at this one. Actually write down number 1 and number 2. You don't have to write down the first line, and understand or feel that every parts of a words that is in this definition. And also look at there's 2 parts of a definition. One is one definition. Second is another definition. So I want you to copy that, not busy copying down, and by this act of writing this one down, try to understand it a little bit better, right? So in your personal note, not in the exercise sheet, write down the first definition slowly and understand each part of it. I think number 1 makes perfect sense, since that's what we just discussed in here. So write them down. I'll give you some minutes. The second condition required to check every number in between -3 and 4. Second condition checked every number. The first condition says they usually give this one. C is 2. Okay, C is 5. And check that. It's continuous at 5. Right? So we'll go through examples and you can probably compare these two again. But let me ask this question. How many numbers are there in between -3 and 4? How many? Infinitely many. That's correct. It's not like, oh, -2 and -1 and 0 and 1 and 2. That's not it. There are more numbers in between, right? So don't think that that's the only number in between -3 and 4. So here, given 1 point, and the second condition again is requiring checking how many values? All values in C. There are usually infinitely many values in this. It's impossible to check with actual. So you start arbitrary, just like we did xn. So that's what we're going to see. All right? So okay, here's one picture before we actually go into any calculation. Is this picture here, and I want you to look at this picture and interpret it as a motion. So this is not going to be spring mass motion. Suppose there's one particle that we can actually detect that with some expensive equipment. So here's a t, right? That's a position ft. Still moving up and down. It's not actually moving like this. Right? I gave you the picture before like this. That was a position. It's a space-time. This is not actually how it moves, right? Actually, how the trajectory of that center of mass is actually going up and down. But if you expand it over space-time, it looks like this. So if you look at it like this, it's not like really this, frog is just jumping over. That's not the motion. It's actually going up and down in here. The actual trajectory is vertical and very simple, going up and down. So, to you, where do you think is rough location of this one? Let's say that was y equals 0. Where is the location in 0.5 second, you think, to you? 0.5 seconds here. Is that right? Roughly there. Would you agree that was roughly about 1.5 units above? Let's say that was 1.5 centimeter above. So above here, y equals 1.5 centimeter. That particle at 0.5 second is measured and observed that it was 1.5 centimeter above the unit, above the 0 unit. Make sense? All right. So that's that. How about f of 1? Where is this particle at 1 second later? If you go 1 second up there, what does it say? It doesn't exist, right? It's empty. So this particle disappeared. We try to measure that 1 second. Where is this? The particle happened to disappear. Whatever the phenomenon we don't understand, it just disappeared, right? So think about it. First, when they're trying to understand the motion of an electron, that could probably shocking. That how can this discontinuously move around? It's made no sense, right? Just accept that sometimes it disappears and appears again. Maybe that's a possibility. Right, what happened to this particle vertically moving in between 1 and 2? If you try to measure, very many time period between 1 and 2 seconds, what is happening to this particle? It's constant. It's not moving. It's always in the same position. You see, everywhere here, it's not horizontally moving. It is always in the position of what? 1 centimeter above It's 0 position. At 1.5 second that's the position. 1.75 second is always in one centimeter above. So between that time period is here and 1 centimeter, not going anywhere. That's what this is suggesting, right? So what happened right after that when t being 2.01 second, right? And it's 2.01 seconds over here. Seems like it's slightly above than 1. It's begin to move upward there, right? And it doesn't go all the way to 1.5, but seems it's reaching somewhere in the 1.25 and coming back down again. So you can any time if you look at this type of graph, you can interpret the motion that's moving vertically up and down, right? For example, if you throw a baseball, look at the center of mass of the baseball and throw it upwards, going up and down, and you can sketch the graph as a graph in this Newtonian space-time. That's the main object thing to study in this course. Look at the graph and analyze it in here, right? So is this motion continuous motion? There's a little weird thing. It disappeared, right? Disappeared. So there's a kind of hole in there. That's one example. There's a hole in there. It's example of a discontinuous function. It's discontinuous on this entire interval, 0 to 3. We looked at it as a whole thing is 0 to 3. And there's a problem at 1. But what do you think is about between 1 and 3? Between 1 second and 3 seconds. It doesn't even include 1 second, right? Do you think there's a problem spot in between here to there? So it all seems like nicely connected and all that, right? So I would say this seems like continuous. Right? There's no break and things like that. Another example of discontinuous thing is that a graph going up, keep going up and vertically, and disappeared. And it showed them at the bottom on the next moment, and then keep going up, right? As if it is some video looping to itself all the time. So this thing is dot is going up and disappeared and showed the bottom again and disappeared and showed the bottom again. That the picture of that motion is going to be like this, right? In the space-time. So this is also discontinuous because of the break and it's introduced there. So that's a common picture of a discontinuous function, but that's not how you mathematically establish that, oh, here's a look at the picture of this graph that looks like discontinuous. That's not how you do it. You go through this definition mathematically and establish, and that's how I'm going to show you. But it's good to have that that kind of insight and understanding in the pictorial term, right? Whenever it says show or prove this is continuous, discontinuous, no pictures, you have to deal with these lines. Okay? Yes, Derek.